Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about Markov chains, which are an extremely popular model that is applied to time series data. We will explain the logic for the conditional independence assumptions that underlie the Markov chain model, and then we will describe its properties. Let's get to it. We're going to talk about Markov chains, and the goal is to model time series data where each data point is associated to a certain time. Okay, and they're usually ordered so that time goes in this direction. Xi represents the data point at time I. Here you can see some precipitation data, some hourly precipitation data. So we have a measurement at each hour that tells us whether there's precipitation or not. Naively, before I lived in New York, I would have assumed that this must be rain because it's April, but it actually unfortunately snows in New York, to my horror, relatively often in April. Anyways, so we have this data and now we want to model it. So our first idea could be, okay, so let's represent precipitation at each time by a random variable AI. And now we want to estimate the joint PMF of these random variables. Okay, so far so good. This sounds pretty easy to do. So how many entries does the joint PMF have? So in our case, we have precipitation, it's 0, 1. Like this is actually pretty easy. So we just need to figure out how many possible sequences of zeros and ones we have for these n data points. If there was just one data point, the possibilities would be 2. If there were 2, it's 0, 0, 0, 1, 1, 0, 1, 1. It's 2 to the power 2, 4. If there's n, it's going to be 2 to the power n. If you check out the video on the curse of dimensionality, you can imagine this as a tree going down that gives you all the possibilities in the leaves. So we have 2 to the n. If we have 100, only 100 data points, which is not that crazy. Actually, it's a relatively small data set. Now the possibilities are 10 to the 30. The entries in the joint PMF are 10 to the 30. So we can start forgetting about this, right? This is completely intractable. Even if we had many time series for the same data points, like we're never going to have enough data to estimate this full joint PMF. We talked about this in detail in the video on the curse of dimensionality. This is a fundamental challenge in probabilistic modeling. It's impossible. We need some additional independence or conditional independence assumptions in order to be able to model our data. All right, so let's accept that. A very simple possibility would be to assume that the data are IID, like we often do when we're estimating PMFs or PDFs. And they all have, so what does IID mean? It means that the data are independent. So the joint PMF factorizes into the product of the marginal PMFs. It also means that they're identically distributed. So they all have the same PMF. So then our life becomes really easy because the joint PMF factorizes into a product of the same PMF multiplied n times, evaluated at the n observations. How many parameters do we have here? We just have one parameter, right? It's the probability that it rains or not. Okay, this is what we're saying, where we're saying that we have the same probability of precipitation or not at each point, and they're all independent. We're not modeling any dependencies. So the good news is that this is super tractable. This is very easy to do with the data that we have. The bad news is that we're not modeling temporal structure. So what are we doing here? Okay, it's absolutely crucial to model temporal structure for almost anything you want to do with this time series data. So this model is tractable, but it's just too simple. It's not going to work. Okay, so how about we want to model some dependencies. The most important dependencies are the transitions, right? What happens at time I given time I minus 1. Okay, that's probably the most important dependencies that we should incorporate in our model. We can't incorporate too many because otherwise things will become intractable. So this is the simplest thing we can do while incorporating some transitions. We're going to assume that there's conditional independence. So basically, if we're interested in what's going on at time AI plus 1, we're going to assume that if we know what was going on just before, we don't need to worry about all the past history. That basically is the simplest way that we can model the transitions, avoiding this explosion of dependencies in our model. That's called the Markov property. Okay, so again, what's going on at time I plus 1 is conditionally independent of everything that goes before, as long as we know what happened right before, as long as we know what happened at time I. So why is this useful? What we're saying is that the conditional probability of AI plus 1 given the past is essentially always equal to the conditional probability of AI plus 1 given the previous data point. That is very, very useful because when we consider the full joint PMF, well, we run into this issue, right? Like if we look at the full PMF and we apply the chain rule, what happens is that at the beginning things are pretty easy. We have the marginal. We can definitely estimate this from data. This is a one-step transition. We can definitely estimate this from data. We can probably estimate these two-step transitions, unless the number of data points is really, really very small. But soon, as we condition on more and more values, this is going to explode. Okay, we're going to have many, many, many conditional PMFs, different conditional PMFs, right? Because these PMFs depend on what we're conditioning on. And this is the whole previous sequence of precipitation or not precipitation in our example. The number of possibilities are going to explode. We're not going to have enough data to be able to estimate all of these conditional probabilities. However, under our Markov assumption, life suddenly becomes much better because this simplifies to just what happened before. So now we only have to consider the conditional probabilities of what happened if before it rained or not, or there was precipitation or not, as opposed to what happened, the conditional probability if there's a certain sequence of a very long sequence before, like rain, no rain, rain, no rain, which would be impossible to estimate from all the data. Okay, I hope this last part maybe was a little bit confusing. I hope it's clear. I hope that you see that the joint PMF is intractable if we consider all the possible dependencies, but if suddenly we apply the Markov property where each time point only depends on the previous one, then suddenly the joint PMF has a factorization that is much simpler. Okay, so this is our third idea. We have this Markov chain model where we're just modeling one-step dependencies, one-step transitions. In order to obtain the full joint PMF, we just need the PMF at the beginning and then the PMF of each data point given the previous one. So how many parameters do we need to estimate? We need to estimate one parameter for this guy and two parameters for this guy because we need to condition on precipitation and also on not precipitation. So there's two conditional PMFs here. And we do have to do that for n-1 data points. For the first one, we're just doing this, right? So 2 times n-1 plus 1, it's 2n-1. So this has reduced the number of parameters from 2 to the n, which is insane, to 2n-1, which is much less. Sounds quite tractable. In this case, though, we are assuming that we have a single time series. If we had more time series, we could just try to fit this model this way, but we only have n data points, so it's going to be impossible to fit the two n-1 parameters. We need a model that is even simpler. So now we can take inspiration in our IID model, which was way too simple, but there was an ingredient to it that is going to be useful to us, which is that we assume that each of the marginals were the same. So maybe we can do the same here, but with the transition probabilities. So now we're going to assume that these transition probabilities are all the same. In this previous model, we weren't assuming that. So the transition probabilities could be different, let's say in January than in June, which is probably true. But again, we don't have enough data to account for that. If we had data from many, many, many years, you might want to do something like that. Okay, so now we're going to assume that the transition probabilities are all the same, and our life is going to become even easier. So again, like these conditional probabilities of the point at I plus 1 given the point at I, we were assuming that they could be different. Now we're going to fix them to all be the same. So when we do that, we get this joint PMF. We apply the chain rule. We apply the Markov property. So now we only care about the one-step transition probabilities. And now we're going to assume that they're all the same. So boom, suddenly the number of parameters in our model is actually extremely small. In fact, for the precipitation example, we just need to know what's the probability of precipitation or no precipitation at first. That's one parameter. And then we need to know the transitions when there's precipitation, so that's another parameter, and when there's no precipitation, so that's another parameter. So we only have 3 parameters in our model. So this is going to be very easy to estimate from data. So let's take a look. These are the marginal probabilities for our data set of there being precipitation or not. So about 90% of the time, 88.7, it does not rain. 11.3% of the time it rains. With our model, we use the transition probabilities, which are the following. This tells us what happens at our h plus 1 given what's happening at our h. So if it does not rain at h, then the probability that it does not rain at h plus 1 is 96%, very different from this 89%. Okay? If it does rain, then the probability that it also rains afterwards is almost 70%. Compare that to the marginal probability. So knowing that it has rained is extremely informative about what is going to happen next. Extremely informative. You will probably want to include this in your time series model. You might be saying, well, this one-step model seems extremely simple to me. Maybe you would want to incorporate like another step. So let's see what happens if you do that. Here we're seeing what happens at h plus 1 when you condition on both h and h minus 1. So it's like a two-step model. So first, if there's no precipitation at h minus 1 and it doesn't rain at h, then the probability that it doesn't rain at h plus 1 is 97%. Compared to 96%, we're not gaining much, okay, with this additional information. What happens if it does rain at time h, but it did not rain at h minus 1? Now the probabilities are kind of different to this probability. So you are gaining some information, but it's much less dramatic than this jump, okay? So this jump is completely dramatic. If it's raining at the previous time, then the probability that it's raining now is actually, goes from 10% to 70%. If you know what happened 2 steps back, you would moderate it to 50% if it's not raining 2 steps back, and you would change it to 77% if you know that it's raining 2 steps back. The changes are much smaller, okay? Here, if there was rain so let me erase this just to finish this. If there was rain 2 steps back, okay, and it doesn't rain, then these probabilities also change quite a bit from these ones. But again, it's really not as dramatic as the change that we see from marginal probabilities to 1 step. So you gain a lot modeling these 1-step transition probabilities, not so much when you go from 1 step to 2 steps, although you gain something. And this is often the case in probabilistic modeling. The gains that you obtain by modeling more dependencies usually have diminishing returns. Okay, so now to show you an example of these diminishing returns, let's imagine that I want to use this to predict precipitation in 2016. I'm going to use these 3 models. So the first model, I want you to think about this, so maybe pause the video. How do I use this model to predict what's going to happen at each hour in 2016? And the answer is using this model, I have to say it does not rain at any point. What is the test accuracy of this model? It's 83%, okay, because the precipitation in 2016 was not the same as in 2015. So the accuracy is not 88, it's not 88.7%, it's less, it's 83.4%, okay, just because of differences in precipitation from one year to the other. Okay, perfect. That's a pretty dumb model, but it actually does reasonably well just because precipitation doesn't happen that often. Now, how do I use my 1-step conditional probability model, my Markov chain model, if you want? Think about it. So what am I going to do? I'm going to see what's happening in the previous hour. If it doesn't rain, I'm going to say that it won't rain in the hour after. And if it does rain, I'm going to say that it does rain in the hour after. Okay, so my model requires knowing what happened the hour before, and it will basically say that things are going to stay the same. How well does that model do? Better, 87.3%. And remember that, most of the time there's no precipitation, so this increase in accuracy is actually pretty substantial. Okay, so we have like a very substantial gain by modeling 1-step conditional probabilities. Now let's see what happens if we use 2-step conditional probabilities. So let's see first what our estimate is going to be. when there's no precipitation at times h minus 1, if there's no precipitation at times h, we say no precipitation. If there is precipitation at time h, then we actually say that there is going to be precipitation at h plus 1 because it's slightly bigger. Okay, this number is slightly bigger. What happens if there's precipitation at h minus 1? If there's no precipitation at h, we say that there's no precipitation at h plus 1. If there is precipitation at h, we say there is precipitation at h plus 1. And if you're paying attention, you will realize that we don't care about what is happening at time h minus 1. Okay, whether there is no precipitation or there is precipitation, we essentially say basically we say that if there's precipitation at times h, there will be precipitation at times h plus 1. If there's no precipitation at times h, there will be no precipitation at time h plus 1, just because of how the conditional probabilities are structured. So we have the exact same estimate. Here, I have to tell you, like we're making these hard estimates. That doesn't make a lot of sense. You would probably want to say, oh, this is the probability that it's going to rain, and you would have to evaluate this in another way. So this is a cartoon example, but it does reflect the fact that modeling 2 steps back actually does give you diminishing returns, because obviously your test accuracy is going to be exactly the same as here, just because it's the same rule, the same prediction rule. Again, this is probably not the best way of evaluating weather prediction. It's just a cartoon example, but it does reflect the fact that modeling one-step transitions is extremely powerful, and that there's diminishing returns on modeling more transitions oftentimes. Okay, so we're going to, like this model that we just designed had 2 possible states at each time. There was either precipitation or no precipitation. Markov chains where this happens, where you always have the same number of possibilities at each time step that represent the same possibilities, which we call states, are called finite-state Markov chains. So each entry in a Markov chain takes a value in a finite set that is always the same. So in the case of precipitation or no precipitation, that would be precipitation or no precipitation, okay, 0 or 1. The Markov chain always takes values 0 or 1 for every time step. We can represent the marginal PMF at a certain time of this random vector as the probabilities that we are, by the random vector, I mean, of course, the whole Markov chain from time I up to time n. If we just look at the marginal PMF of one of the entries at time I, then we can basically put the probabilities that compose that marginal PMF into a vector. So here, in the case of precipitation and no precipitation, we would just have probability of no precipitation and probability of precipitation. If we have m states, we will have m entries in this vector. What is the sum of the entries of this vector? Again, maybe pause and think about it. It has to be 1 because this is a PMF. It's a marginal PMF at time I. Okay, I denote it with this pi I notation. Okay, so when we're going to be considering time homogeneous finite state Markov chains, as in our rain example, where we assume that the transition probabilities between states are always the same at every time. So when we look at the conditional probability at time I plus 1, given what's going on at time I, well, I don't know what I'm doing there, given what is going on at time I, they're always the same. This means that we can put them into a transition matrix. So this transition matrix essentially tells us the probability that when we leave state S1, we go to state 1, state 2, state M. Notice that we have to go somewhere. So here the columns are going to add up to 1. Okay? In the literature, you might see transition matrices that are the transpose of this, where the rows add up to 1. In a moment, you will know why I prefer this notation, but just don't be surprised. Okay? If you find that the definition in some books is the transpose of this, where the rows add up to 1. So in our case, we had these transition probabilities from precipitation to no precipitation, and so on, and we can put them into a transition matrix, where here we have the probability of going from no precipitation to no precipitation or to precipitation. And here we have the probability of going from precipitation to no precipitation. I wish instead of precipitation, this was just rain. And I could just say rain because I'm a bit tired of saying precipitation, but that's what it is. Okay, and here this is the probability of going from precipitation to precipitation. All right. Luckily, we're going to move to another example, so I won't need to say precipitation again. We're going to take a look at an example where we're modeling a car rental that operates in California. This is a made-up example. And basically, this car rental maybe hires you as a data scientist to try to figure out how the different cars that they rent out are going to move along 3 locations that they have: LA, San Francisco, and San Jose. And basically, the customer can take the car in one of the locations, drive to another one, and leave the car there. From past data, we observe that if cars that start in San Francisco stay in San Francisco 60% of the time and then move to LA 20% of the time and move to San Jose 20% of the time. Cars that are in LA stay 80% of the time and they move to the other 2 places 10% of the time, and so on. Okay, and we're going to model this as a Markov chain. It's often useful, just for visualizing the transitions between Markov chains, to draw them as state diagrams. So here we can see that from San Francisco, there's like 60% probability of staying in San Francisco, 0.2 going to LA, 0.2 going to San Jose. For San Jose, there's 40% of staying, 30% of going to LA, 30% of going to San Francisco. Okay. So now we're going to take a look at the state vector and transition matrix for this Markov chain that we're using to model the car rental. We're going to assume that cars are initially allocated to each location with the same probability. What does that mean? It means that at time 1, the state vector just has 1/3, 1/3, 1/3, because that's the probability of being in San Francisco, LA, and San Jose. And the transition matrix just contains those transition probabilities that we just explained, that tells us what's the probability of staying in San Francisco, going from San Francisco to LA, going from San Francisco to San Jose. So again, the columns add up to 1. This is a possible realization. This is a car that starts in San Francisco. I simulated this using the Markov chain assumptions. Jumps to San Jose, comes back to San Francisco, jumps to LA, stays in San Francisco for a while. This is another example that starts in LA, goes to San Jose, comes to San Francisco, I'm in New York now, I don't know why I said that. Goes to San Jose again, and then stays in LA. I used to live close to San Francisco, so maybe that's why. Again, starts in San Francisco, goes to LA, ends up in San Jose for a while. These are just examples of realizations sampled from this Markov chain. All right, so how do we compute probabilities using our model? Just as an example, let's compute the probability that a car starts in San Francisco, is in San Jose, and then is in San Jose after the second customer. Okay, so we want to know the probability that you start in San Francisco, and then at time 3, you're in San Jose. 3 represents San Jose here in our states. Okay, so what are we going to do? We need to, as usual, this is a good practice for when you're doing homework problems or probabilistic modeling in general. You need to see what information you have and what you want. Typically, this will involve identifying the variables that are not here that we want to include. And we definitely want to include what's happening at time 2, because we're assuming that this Markov chain has this structure where we know the transition probabilities given what happened just before. So we need to include what's happening in time 2 here. We can do this just by applying the fact that the marginal of A1 and A3 is just equal to the joint PMF summed over the variable that we don't want, which in this case is A2. So we're seeing what happens if we go through all the possibilities for the second step. Okay, San Francisco, LA, and San Jose. Okay, so now what are we going to do with this joint PMF? We're going to apply our Markov assumption. And in the right direction, right? Because here, this is an instance where it's extremely important in what direction you apply the chain rule. You want to definitely take out P of A1 first, then P of A2 given A1, and then P of A3 given A1 and A2, which is just equal to P of A3 given A2 under the Markov assumption. Okay, if you take out, P of A2 first, nothing is going to work out. Okay, so now we have these transition probabilities. We can just plug in the values, the corresponding values of the transition matrix, and you can, and again, we're summing over the possibilities of going through the 3 different cities, and we get that the probability is approximately like 7.3%. Okay, so this is just an example about how we can use the transition matrix and the state vector to compute any probability that we're interested in concerning this Markov chain. So now we're going to see that this can be done in a much more systematic way. So let's take a look at what the state vector at time I actually equals to. So again, the state vector at time I contains the marginal probabilities of being in each of the states at that time. So what is this probability of being in state 1? Well, it's basically the probability of being in the different states at time I minus 1 multiplied by the corresponding conditional probability, and then we sum them all together. If we want the probability of being in San Francisco, we see what's the probability that we were in San Francisco and we stayed, we were in LA and we moved to San Francisco, we were in San Jose and we moved to San Francisco. Okay? We can actually express that in terms of the previous state vector, right? All this is we take all the possibilities in the previous state vector and we multiply them by the corresponding conditional. So here I drew too many lines, so let me go back. We take the probability that we're in San Francisco and we multiply it by the probability of staying. We take the probability that we were in LA, probability of moving from LA to the state that we're interested in, and so on and so forth. And maybe you can see where this is going, because when we look at the probability of being in the second state, we're doing exactly the same thing, okay, except that now we look at the conditional probabilities of moving towards that second state. So we have exactly the same previous state vector here, but now we change the conditionals to be with respect to the second state. What are we going to do for the rest of the states? Exactly the same thing. So we're just basically going to multiply the previous state vector by this matrix that contains all the conditional probabilities. And now you can see why I arranged them in this way, where these guys add up to 1, because this way I can express the state vector at time I as the transition matrix times the state vector at I minus 1. If you use the transpose, then basically you have row vectors, you have to multiply on the left. I don't like doing that, but to each his own. You will find books that do that. Okay, but me, I like multiplying matrices on the left of vectors. This is great because now it's super easy to compute these probabilities. If you know the state vector at a certain time, you just have to multiply by the transition matrix to find the state vector at a later time. So for example, the state vector at times I is equal by what we just explained to the transition matrix times the state vector at times I minus 1. But now we can continue, right? It's this guy is equal to t times the state vector at I minus 2. So we can go all the way back and see that the state vector at time I is just can be obtained by applying the transition matrix I minus 1 times to the first state vector. Okay, so this gives us a very easy way to describe the evolution of the state vector over time. So for example, imagine that we're interested in what happens with the 5th customer. We know that the state vector at time 1 is equal to this. We know the transition matrix. So basically, after the 5th customer, which is time 6, okay, because we always check what happens after each of the customers, we just need to apply t 5 times. So we multiply this matrix 5 times. You can do it by hand, but I just use Python for this. And we get that state vector immediately. So we have a very easy way of computing, again, the evolution of the state vector over time. Okay, so what have we learned? We have learned why we use Markov chains to model time series. We make these conditional independence assumptions that might seem very naive at first, because of course the past history must matter to some extent, but you need to realize that because of the curse of dimensionality, it's just impossible to model the full dependencies. You need to choose wisely what dependencies you're going to put in your model, and hopefully they're going to be useful. And what we saw is that in time series, you typically have a huge gain from modeling one-step transition probabilities, and usually less from modeling more steps. But this will depend on the application. Then we explored the basic properties of Markov chains, in particular of finite-state, time-homogeneous Markov chains that are fully characterized by their state vector and their transition matrix. And that's all I got. Thank you very much.